Good morning to my morning classes. Good afternoon to my afternoon class. Today we are learning independent event probability. But first, let's have a quick review on our law of large numbers. The more trials I do, the farther away from the theoretical probability I get. Is this true or false? Again, this is definitely false. Remember, practice makes perfect. The more trials you do, the closer to the theoretical probability you will get. So again, today we're learning about independent event probabilities. I pledge allegiance to the flag of the United States of America and to the republic for which it stands, one nation, under God, indivisible, with liberty and justice for all. A quick recap on this week. Today we're doing independent event probability, which is in this Edpuzzle. You will have a homework to go along with it. Tomorrow you have kind of a free session during when you would have math. I will send a link for homework help for the first two homeworks from the week, and we will work on these two homeworks next Friday. So we've learned already about independent and dependent events this year. Today we're going to look at them in regards to probability. An independent event is an event whose outcomes are not affected by the outcomes of another event or events. For example, if you flip a coin 5 times, it doesn't matter how many times you flip that coin. One is not going to affect another on if you get heads or tails. So just because you get heads the first time, that's not going to affect what you'll get on your second flip, your third flip, and so on. Dependent events are events whose outcomes are affected by the outcomes of other events. So for example, if you have a bag of chips and you pull a blue chip out of a bag of 5 and you don't put it back, you now will change the probability of pulling a blue chip on your second pull, because now instead of having 5 chips, there's only 4 chips because you didn't put it back. So your second probability will be dependent upon your first probability's outcome. It will have an effect. Let's look at this in a scenario. Let's say you and a friend are pulling marbles from this bag. So you can see we have 2 green marbles, 2 blue marbles. Okay? You pick a blue marble and then you put it back. So the probability of you pulling a blue was 2 out of 4, or 1/2. Now it's your friend's turn. We can calculate that the probability that your friend will pull a blue is also 2 out of 4, or 1/2, because you put yours back. So there's still 2 blue marbles out of a total of 4 marbles. Scenario number 2. This time you pick a blue marble, but you don't put it back. So your probability of picking a blue marble is still 2 out of 4, or 1/2. But now when your friend goes to pull a marble, now there's only 3 marbles left in the bag, and only 1 of those is blue. So the probability of your friend being able to pull a blue marble is now 1 out of 3. So notice that because you didn't put your marble back, the probability for the second pull has changed. We changed both the favorable outcomes and the total outcomes. So which of these two scenarios do you think was the independent event? Scenario number 1, where you did replace the marble, or scenario number 2, where you did not replace the marble? Which was independent? We can see that scenario number 1 was the independent event. The occurrence of one event does not affect the probability of the other. So because you put that marble back, you haven't changed anything. Each drawing, yours and your friends, were independent of each other. Scenario number 2 was a dependent event. Your first pull was independent, but your friend's pull was dependent on yours. Because you didn't pull that marble back, you changed their probability. So here's a few examples of independent events. If you roll a number cube or a die and you get a 2, that result will not change the probability of then getting a 3 if you roll that die again. The probability is always going to remain 1 out of 6 for rolling each number on that cube. Same thing with tossing a coin. If you toss a coin and you get tails, that doesn't change the probability of getting heads when you toss the coin again. Your probability will still remain 1/2. So here's an example. 2 experiments are being conducted with a bag that contains 4 blue marbles and 3 yellow marbles. The question for both experiments is, what is the probability of drawing a yellow marble? So let's take a look at our independent experiment. Here we're going to draw 1 marble, record the result, and put the marble back in the bag so we can then draw another marble. So if we look here, if I want to know the probability of drawing yellow, I have 3 yellow marbles out of a total of 7. So if I pull it out, I get a yellow, record it, put it back. I still then have a chance of 3 out of 7 to draw a yellow marble again. I haven't changed anything here. This is an independent experiment. If I did a dependent experiment here, now drawing 1 marble, recording the result, but then not putting that marble back before I pick a new marble. So here, let's assume that our first marble drawn is blue. So if I draw my blue marble, my chances of drawing a blue marble are 4 out of 7. Now I don't put that marble back. So for my second draw, we'll put for blue. My second draw, it wants me to draw a yellow. Remember, it said at the beginning, we want to know probability of drawing a yellow. So this is now my second draw, and I want to draw a yellow. Well, because I took that marble out and I didn't put it back, that blue marble that we took, there's now only 6 marbles left in the bag. So I can pull 3 possible yellow out of now a new total of 6. So we are now down to a 1/2, 3/6 or 1/2 probability instead of 3/7. You see how that changed because we didn't replace that marble? Let's try some here. The numbers 1, 2, 3, 4, 5, and 6 are on the sides of this number cube. Mike rolls a 2. If Mike rolls the number cube a second time, he wonders what the probability of rolling 2 again will be. Is this an example of an independent or a dependent probability? This would be an example of an independent probability. Okay, so rolling this number cube, just because he got a 2 the first time, that is not going to change his options of getting a 2 the second time. We didn't take anything away. We didn't change our total possible outcome. Each card below has one of the following letters on the other side: A, B, C, D, E, F, G, and H. Rita picks a G and keeps it. If Rita picks another card from the cards that are left, she wonders what the probability of picking C will be. Is this an example of an independent or dependent probability? This is an example of a dependent probability event. If Rita picks a G and then she takes it away, there's no longer 8 cards to choose from. Now our probability of picking a C is going to be 1 out of 7 because she took that 8th card and never put it back. So her probability has changed. So we're going to focus now on just independent events. To find the probability of 2 independent events both happening, we first find the probability of each, then multiply the 2 fractions together to find the probability of them both happening. Remember, when they are independent events, one event's probability will not affect the others. Wanda spins the spinner 2 times. Find the probability of landing on a tree on the first spin and on a flower on the second spin. So remember, we want them both to happen. So that word "and" here is a huge clue. When you see "and" in these problems, it means we need to multiply our probabilities. So we're going to start by finding the probability of the tree. So there's 1, 2, 3 trees out of a total of 8 options. And we're going to multiply by the probability of our flower. There are 5 flowers out of 8 options. Remember, when you're multiplying fractions, you multiply numerator times numerator. 3 times 5 is 15. Denominator times denominator. 8 times 8 is 64. So our probability of getting a tree on the first spin and a flower on the second spin is 15 out of 64. To find the probability of either of two independents happening, we first find the probability of each. Then we add these two together to find the probability of either of them happening. So when we're looking for either, we're going to use the word "or." That's our key word here. Justin spins the spinner only once. Find the probability of landing on a tree or a flower. So "or" is going to mean add. All right, so if it's "and," it's multiply. If it's "or," it's add. So again, our probability of a tree, 3 out of 8. Our probability of a flower is 5 out of 8. Now remember, when you're adding fractions, you add the numerators. If your denominators are the same, add the numerator. 3 plus 5 is 8, and keep the denominator as itself. So we get 8 out of 8, or in this case, 1. Well, our only options here are trees and flowers, so that makes sense that you have a 100% probability of getting a tree or a flower. Let's practice. Alexandria spins the spinner once. Find the probability of landing on a cat or a bird. Remember, that word "or" means what? Add or multiply. The word "or" means to add, so we're going to add our probabilities here. The probability of a cat is 3 out of 8, plus the probability of a bird is 1 out of 8. So what's our total probability here? When you add these together, 3 plus 1 is 4 out of 8, or you could have also said 1/2. Patricia spins the spinner 2 times. Find the probability of landing on a flower on each spin. So now our keyword here is "and." We want them both to happen. And remember, "and" means multiply. See if you can do this whole problem. All right, so the probability of a flower is 5 out of 8 times, again, probability of a flower, which is 5 out of 8. When we're multiplying, numerator times numerator, 5 times 5 is 25, and denominator times denominator, 8 times 8 is 64. So our probability of spinning a flower on both spins here would be 25 out of 64. Find the probability of tossing heads with a coin and landing on a 4 on a spinner labeled 1 through 8. So look for that keyword there of and you have to think, am I going to add or multiply? Remember, "and" means multiply. So the probability of tossing heads is 1 out of 2. You can get heads or tails. And of landing on a 4 is 1 out of 8. 1 times 1 is 1. And 2 times 8 is 16. So our answer here is C. If you have any questions, please send me an email. You did a great job today. Your homework is independent event probability.